In this section, we're going to talk about solutions by substitution. We're going to make some substitution, and then we will be in a better position to solve the differential equation. But first, we have to get a definition out of the way. If our function f has the following property. Has the property that f of tx comma ty, so this function f is a function of two variables. If this is equal to f of x comma y times, notice that both of these have a t in it, times t to some power. And what's t, or what's alpha? For some alpha in the real numbers. That is, alpha can be any real number, doesn't matter. If that's true, then we say that f of xy is a homogeneous function. Of degree alpha. Of degree alpha. Let's look at an example. Suppose f of x is equal to suppose f of xy is equal to 1 over x squared plus 1 over y squared. So basically, let me just write this a little bit bigger, because I'm going to talk big times about what's going on in the brackets. If you do 1 over the first entry squared, which is this, and you do 1 over the second entry squared is that, and you add them, that's f of xy. I mean, for example, f of 3, 4, we take this 3, we square it in the bottom, we put a 1 on the top. We take the 4, we square it on the bottom, we put a 1 on the top, and we add them. And you get whatever you get. So we want to look at f of tx comma ty. So the first entry is tx and the second entry is ty. The entries are separated by the comma. So I take the first entry, I square it in the bottom, I put a 1 on the top. I take the second entry, put it in the bottom, square it, put a 1 on the top, then I add them. Well, this is 1 over t squared times x squared plus 1 over t gets squared times y gets squared. So t squared y squared. Now, it turns out that the 1 over t squared is common. 1 over t squared times 1 over x squared gives me this. Plus 1 over t squared times 1 over y squared gives me this. So this part I'm just going to rewrite differently. I'm going to write it as t to the negative 2 times this, times that. But that is f of xy. F of xy is this. But this is exactly what I have here. So it's t to the negative 2 times f of xy. So so this implies that f of xy is a homogeneous function of degree -2. Of degree -2. It clearly said in the definition for some alpha in the real numbers. That power is the alpha. It can be any real number. The f of xy is a homogeneous equation. So we just defined what a homogeneous function is. In a way, you can factor out the t. You can factor out the same thing from both of them, but you might get some power other than 1. Okay. Now, another definition. A first order differential equation in the form m of x comma y dx plus n of x comma y dy equals 0 is said to be homogeneous if m and n, these functions, if m and n are both homogeneous functions of the same degree. Okay. I want to comment on this part. It's said to be homogeneous. That is not homogeneous as before. Notice it doesn't say homogeneous equation. It's not the same. And the degrees is not enough for m and n to both be homogeneous functions. They have to be homogeneous functions and of the same degree before we call it homogeneous. This homogeneous is a different homogeneous than before when we talked about homogeneous equations. Okay. So this would mean that if you look at m of tx, ty, the t's kind of factor out and you get m of xy. But the t gets raised to some power. Now, when it comes to the n of t of x, t of y, once again the t to some power factors out times n of xy. For this equation up here, it must be true to be, for that equation up there to be homogeneous. For this equation here, for this differential equation, the one that I'm boxing in red, for it to be homogeneous, it better be that m is a homogeneous function of degree alpha, and n is also a homogeneous function of degree alpha. These powers of t have to be the same. It's not enough for them to m and n to just be homogeneous. It is not enough. Homogeneous function. They have to be homogeneous functions of the same degree before we'll say that this function, this differential equation, is homogeneous. Okay. Now, let's look at something interesting. Suppose m and n are both homogeneous functions. Suppose that they're both homogeneous functions. Well, we can play a game with this. We can play a game here because m of xy is equal to m of, well, x is the same as x times 1, and y is the same as x times y over x. So what's common in the common factor in each of those two expressions is x. So we can factor out, since m is homogeneous, we can factor out the x. It'll be x to some power. And then we're left with everything, 1 comma y over x. 1 comma y over x. And the same game with n. You have n of xy. Well, that's n of x times 1 comma the y. I'll think of as y times y over x. Just in case you didn't see it, these x's cancel out, and you do get back y. We should get back y. And that's exactly what that product is. Okay? But now, it's a homogeneous function to anything that's common. Remember, when we had m of tx comma ty, the t is common. They kind of factored out, you can think. So you have t times m of xy. But they don't exactly factor out. The t's don't exactly factor out. It can factor out as t cubed, for example. Think in my first example that's still in front of us, what factored out was 1 over t squared. Okay, now what's going to happen is we're going to get a separable differential equation. We're going to get a separable differential equation. We'll try to write it up here to save space. But remember, we have m times dx plus n times dy equals 0. But m of xy is that. It's x to the alpha times m of 1 comma y over x. Plus, it does say plus n of xy, but n of xy is this. Oh, I guess I didn't finish. The x's factor out, and you get x to the alpha times n of 1 comma y over x. So you get x to the alpha times n of 1 comma y over x. And this equals 0. Now, the nice thing is, well, I do have one error, or two errors. This should be dx, and that should be dy. Now, I can divide everything by x to the alpha, and when I divide this by x to the alpha, it cancels out. When I divide this term by x to the alpha, it cancels out. And when I divide 0 by x to the alpha, I still get 0. So the equation I have after I divide by x to the alpha is just this equation. dx plus n dy. Put the dy in there nicely. Now if I make a substitution, if I say u is y over x, well that implies that ux is y. Ux is y. Now this here will imply, now I'm going to take the differentials with respect to x. Maybe I'll lie. I'll take the derivatives with respect to y. With respect to x. The derivative of y is dy dx equals. Here I have a product. Take the derivative of u first. Or let me keep u and then I'll take the derivative of x, which is 1. Plus, I'll keep x, and now I will take the derivative of u, which is du dx. Now, if I multiply every term by dx, if I multiply all these terms by dx, when I multiply this by dx, I just get dy. U times 1 is u. If I multiply it by dx, I get u dx. If I multiply this by dx, I'll just get plus x du. Now, let me just show you how easily you can do that. Instead of writing dx on the bottom, I take just differentials. And what's going to happen is the following. When you take the differential of y, you get dy. And here I have a product. So first I'll take the differential of u, I get du, times the second factor. Plus, now I'll just keep u, and I'll take the differential of dx, which is dx. And that should be exactly what I have. Okay, so let me write that down right here. We have that dy is u dx plus x du. And then we're going to substitute this stuff in here. So instead of y over x, I am going to put u. So I have m of 1 comma u dx. I put m 1 comma u dx plus n of 1 comma u times dy, which is this, u dx plus x du, and it equals to 0. Okay, let's just get a little bit more space going, more on the bottom that is. And what I'm going to do is I'm going to distribute. I have m of 1 comma u dx plus this times u dx. I write the u first. U times n of 1 comma u dx plus that product. I write the x first. N, or x times n of 1 comma u du. And this is equal to 0. Okay. Let's see what we have. We have this term plus this term plus that term. And these two terms both have dx's. So I could factor out the dx. I have m of 1 comma u plus u times n plus u times n of 1 comma u. And this all gets multiplied by dx, the common factor, plus x times n of 1 comma u du equals 0. Now notice that m of 1u is only a function of u, and n of 1u is only a function of u. So this is separable. I'm going to bring this term to the other side. So I have m of 1 comma u plus u times n of 1 comma u dx, and this is equal to negative x times n of 1 comma u du. Now, I want to get the x's on one side, and I want to get the du's on the other side. Since this has u's, and the du's on the right side, I'm going to move this factor. It's in the top, and move it to the bottom. It's going to become m of 1 comma u, which is a function of u, plus u, which is a function of u, times n of 1 comma u, which is a function of u. This negative x, I'm going to put it down here, except I'll just put the negative on the top. And I want to move this du over a little bit. I'm going to keep it in the numerator, but I'm going to move it over. And this piece, n of 1u, it's a function of u, so it stays on the u side. Notice, that's a function of x, and this is a function of x. And if I just happen to integrate these, it's separable. It will always be separable. Now, one quick comment. I most certainly made this substitution here. We also can always choose to say v is x over y. And that would imply that yv or vy is equal to x. This is an alternate substitution that we can make. They'll give the same exact results. Absolutely nothing different. Okay. Now, this is definitely not something, this formula at the very bottom, this formula down here, is definitely not something that you should go around memorizing. I definitely don't support that. That is, we should reinvent the wheel every time. Now, I'm going to give you an equation that is homogeneous. So we don't have to check to see if m is a homogeneous function and if n is a homogeneous function, and see if they're of the same degree. But you know, as an exercise we will. As an exercise, we're just going to do just that. M of x squared, m of x comma y is equal to x squared plus y squared. So m of tx comma ty. Now, what does m do? It squares the first component, it squares the second component, and then it adds them. Alright, so I'm going to get tx squared, I'm going to get ty squared, and I'm going to add them up. Well, that's t squared x squared plus t get squared times the y get squared. And I can factor out the like factor, t squared. And what t squared is being multiplied by, x squared plus y squared, that's m. times m of x comma y. That did not work out nicely. Times m of x comma y, which implies that m is a homogeneous function of degree 2. Now we're going to do the same thing for n. That's n, including that sign. N of xy is x squared minus xy. So n of tx comma ty, well, first n squares the first component, then it multiplies the x and y, the two components, and it subtracts them. Alright, whatever. I'm going to square the first component, then I'm going to minus the product of these two components. And I get t squared x squared minus t times t is t squared times x times y. So I get t squared xy. And between these two, I hope this is clear as day that the fact that t squared is coming. So I factor it out, and then what's not in red, x squared minus xy, is what I write down. But it turns out that what's in this bracket is exactly what n is, n of xy. So this t factors out. What this is saying is if anything is common, you can factor it out as that common factor to some power. The power can be any real number. Okay. So this implies that n is a homogeneous function of degree 2. Those two are the same. For this top equation to be called homogeneous, it better be that m and n are homogeneous functions and they have the same degree. So we verified that. Possibly on an exam, you'd have to verify it. So what we're going to do is we'll say that y is u times x, which implies the differential of that is dy. Now I have a product. The differential of the first times the second plus the first, which is u, times the differential of x, which is dx. Whenever you take a differential of a letter, you just put d in front of it. When I took the differential of y, I put d in front of y. When I took the differential of u, I put a d in front of u. When I took the differential of x, I put a d in front of the x. First, you take the differential of u, times it by x, and then you reverse it. Plus, now you just take u, you multiply it by the differential of x. It used to be derivative, now we call it differential. The only difference is we don't write dx. We don't write dx. That's the only difference. So let's rewrite this new equation. Let's rewrite this top equation. And whenever we see y, we're going to put ux. And whenever we see dy, we're going to put this mess. So first I see x squared. So I write x squared plus, then I see y squared. That's how I write y, and I square it, times dx, plus x squared minus x times y. Y is ux, times dy. That's dy. x du plus u dx equals 0. Now let's clean this up a little bit. We have x squared plus u get squared times x get squared dx plus. Let's distribute. We get that product, which is x cubed du minus that product. Well, you have x times another x, that's x cubed, times u du. Times u du. And now, plus, plus x squared u dx, and then minus, well, x times x is x squared. This u here times that u will be u squared times dx, and sorry I ran out of room, but it equals 0. So let's put everything that has dx's. And since everything I'm going to write has a dx, I know dx is going to factor out. We have x squared plus u squared x squared plus x squared minus x squared u squared, and that's all dx's. Now let's write down the u's plus the du's plus x cubed du minus x cubed u du, and that's it, times du, and it equals to 0. Okay. Now, u squared x squared is the same as x squared u squared. We're adding it, and then we're taking away. That part cancels. That part cancels. Kind of surprises me, but it cancels. Okay, now let's see. I meant to write down for dx x squared plus u squared x squared, which is right here, and then x squared u. I didn't write down the u, plus x squared u, sorry about that, minus x squared u. And still I'm not going to disagree that this cancels out. But what I have left, I'm going to write it down here. I have x squared plus x squared u squared. I'm going to factor out the x squared. There's an understood 1 here. X squared times 1 gives me this, plus the x squared in front times u squared gives me that. That's dx. Plus, I'm going to factor out an x cubed here. X cubed times the 1 gives me x cubed minus x cubed times u gives me x cubed u du equals 0. Okay, now we pretty much have a separable differential equation. Let's just go a little bit further. Let's bring this term to the other side. Since it's plus, when it goes to the other side, I have to change the sign. But you know what? I can just change the sign over there. I can say it's x cubed times u minus 1. After all, when this goes to the other side, there's going to be minus in front. When I multiply that minus by 1 minus u, I get u minus 1. Now this is clearly separable. For example, I can move that term, or that factor. I can move this factor under here, 1 plus u squared, and I can move this factor under here. Now this is just x, has just x's, and this just has u's. And this is 100% separable. So let me just write this down on the other side, on another page, and then we'll try our best to solve this integral. So what I came up with is x squared over x cubed dx, and this is u minus 1 over 1 plus u squared du. Now I just want to see one thing. Okay. Now another typo. Sorry about these silly typos. That u is not squared, so it shouldn't be squared. It shouldn't be squared. I'm just dividing by 1 plus u. Now, this is just 1 over x. 1 over x dx. And this is, now, what I like to do here is, when I have 1 plus u in the bottom, or u plus 1 in the bottom, I like to have u plus 1 on the top. Well, I can add 1, but then I have to take away 1. 1 minus 2 is minus 1. And then when I divide this by, I'm just going to call this u plus 1. Well, u plus 1 over u plus 1 is 1 minus 2 over u plus 1. So it's 1 minus 2 over u plus 1 du. An alternative way of getting the exact same answer is to do the division. 1 plus u into u minus 1. This I'm going to write as u plus 1 into u minus 1. U times 1 is u plus 1. And then when I subtract, this cancels, I get minus 2. So it's 1 minus 2 over u plus 1. For the record, u plus 1 doesn't go into 2 or negative 2. That is, that's the remainder. If you notice, it's the exact same thing that we got. However you do it, you have to do it. Now, this integral is just ln of x. And I just feel like putting the constant here. Plus a constant. Ln of c is a constant. But ln of one thing plus ln of another thing is ln of the product. That's what the left side equals. The right hand side. The integral of 1 du, I'm integrating both sides. The integral of 1 du is u. Now, minus, what is the integral of 2 over u plus 1 du? Well, you can pull out the 2, so now you have 2 times the integral of du over u plus 1. But if I call this bottom v, if v is u plus 1, then du would be dv. That is, I have dv over v. So this is 2 times ln of v. But v is u plus 1. And then I will write this as ln of u plus 1 squared. Ln of u plus 1 squared. So this is this. And I will bring this to the other side as plus. So I have ln of this plus ln of that. So I'll have ln of the product. And it still equals the u. Now, we're going to substitute back. And you notice, remember, I said the y is ux. So if y is ux, dividing both sides by x, I come to learn that y over x is u. Alright? So ln of c times x times y, u, which is y over x plus 1. I'm going to write the 1 that way. This equals u. Coming up here, I have cx. What's inside the brackets is an addition with the same denominator. You can just write it as y plus x all over x. Oops. There's an ln in front. There it is. This equals u. For u is y over x. Okay, we're getting there. We're taking ln of this whole mess, and those x's cancel off. So we get yn, or ln, of c times y plus x is equal to y over x. And as far as I can see, that's as far as you can go with this problem. You can't really go any further. Okay, I hate to do this, but another silly typo. Lots of room for error in these problems. That square belongs there, but somehow it didn't come down here. And when I bring this negative ln to the other side, it's going to become plus. So it's going to be ln of cx times u plus 1 squared. And it's still going to equal the lone u. Now what's in here is still being squared. U is y over x, and 1 is x over x. So I do get cx times y plus x over x all squared. Now what happens is this x in the bottom is being squared. I have x squared in the bottom, but I have that x on top. That's going to just be 1 over x. So I still have the c. I have the y plus x squared over the lone x. And that seems to be correct. And we can go further, but I would stop there. There is the answer. Sorry about the silly typos. Let's try another problem. Try not to make some silly mistakes. Suppose you have that x plus y dx plus x dy is homogeneous. That is, m and n are both homogeneous functions of the same degree. Let that be given. Now I have two choices. I can let v equal to x over y, or I can let u equal y over x. Those are my two substitutions. Multiplying both sides by y, we get x is vy. Multiplying both sides by x, we get y is ux. I tend to say those two statements. But personally, I like using this one. Y is u times x, which will mean dy will be u dx plus v plus x du. u dx plus x du. So we have, just copying this or saying this, we have x plus y, but that's how I write y in this problem, dx plus x times dy, which is u dx plus x du, and it equals to 0. Now, if you look at this second line, there's only x's in u's, which means we're doing this right. So we have x plus ux dx plus xu dx plus x squared du equals 0. These two terms have the x's in them. So we're going to factor out the dx. We have x plus ux. We have x plus ux from right here. And then we're adding another xu, which is the same as adding ux. So we'll have 2ux. And this is all times dx. And this I'll bring to the other side as negative x squared du. I want to get the x's by the dx's and the u's by the du's. But I can't do that just yet. I need to factor. Here, I can factor out an x. X times 1 is x, plus x times 2u is 2ux dx. Now, alt factors are either factors involving x's or factors involving u's. The factors are the things that are being multiplied. It's x times 1 plus 2u times dx equals negative x squared times du. Everything underlined either just has x's or just has u's. So I'm going to move them around so the x's and the u's are on the same side. I'll keep this x where it is. I'll move that x into the bottom. I'll keep the du where it is. And I'll move this term, that factor, to the bottom. So I have negative 1 over x after doing this division times dx. And this is equal to du over 1 plus 2u. Now I'm going to integrate both sides. This minus sign you can think of coming out in front. The integral of 1 over x dx is just ln of x. But this minus is really a minus 1. And when you put it up as the power, you get x to the negative 1, which is 1 over x, equals. Now, if I call that v, if I say v is 1 plus 2u, then dv will be 2 du. That is, if I put a 2 in, then that's dv. And this bottom, 1 plus 2u, is v. But if you put a 2 in, you have to bring out a half. There's the half. And I get dv over v. So this is 1/2 ln of v. But that's v. 1 plus 2u. Now, let's add a constant to the left side. So I can always add ln of c. So you have ln of one thing plus ln of another, you end up with ln of the product. 1 over x times c is just c over x. And this half goes up as the power. It's ln of 1 plus 2u to the half. Well, if ln of this equals to ln of that, then does this and does that are equal. C over x is equal to the square root of 1 plus 2u. But u is y over x. So you have c over x is equal to the square root of 1 plus 2u. 2 times y over x. Now I'm going to think of the 1 as x over x. So I have c over x is equal to the square root of x plus 2y over x. Now, this x in the bottom here, I can think of it as square root of x times square root of x. On the right side, I can take the square root of the top and divide that whole thing by the square root of the bottom. Now, exactly what does this do for me? It says, oh, I can cancel off the like factor. Now, if I square both sides, you square c, you just get another c. So you get c over, when I square the bottom, I get x. When I square the right side, I get x plus 2y. Bring the x over, you get c over x minus x is 2y. We just want y divided by 2. And now we're 99% done. I'm going to multiply each term by x because I want to get rid of that x there. When you multiply this by x, you get c. When you multiply that by x, you get x squared. And when you multiply the bottom by x, you get 2x. This is what y equals. That is exactly what y equals. What you learn from these problems is by working them out. Let's do another one. You should definitely be trying to work these out on your own as well. Now I'm telling you that this differential equation is homogeneous. So how about I use the substitution that y is ux, which means dy is u dx plus x du. And u, dividing both sides by x, u is y over x. I use that statement at the end. Okay, so y is ux squared plus y times x dx plus x squared times dy. U dx plus x du. And like it says, it equals 0. Clean this up a little bit. U squared x squared plus u times xx dx plus x squared u dx plus x squared times x is x cubed du. And this equals 0. This is dx and that's dx. So we're going to have u squared x squared plus ux squared plus another ux squared dx. And this is going to equal, bringing that over, negative x cubed du. Now, the first thing I'll say is ux squared plus ux squared is 2ux squared. Now, inside that first bracket, inside here, I can factor out a ux squared. Okay, and after doing that, I get u plus 2 dx. And this is negative x cubed du. The factors are u times x squared times what's in the bracket times dx is equal to negative x cubed times du. Well, dx is on the left and dy is on the right. Go factor by factor. This factor u, I want to cross the division line and put it on the bottom. The x squared, it can stay where it is. The u plus 2, it has u's in it. I cross the division line. It goes from the top to the bottom. The dx stays there. The negative x cubed, I bring it to the other side. So since it's in the top, I put it in the bottom. Okay, let's do a little long division, or do some division. That becomes negative 1 over x dx. And real simple to lose that minus sign, so let's try not to. And this is equal to du over u times u plus 2. So we have negative 1 over x dx, and this is equal to du over u times u plus 2. And you verify that, and I'm happy. So now I'm going to integrate both sides. That minus sign comes out in front, and then I get ln of x. It's the integral of 1 over x dx is ln of x. But that negative, which is negative 1, can go up as the power, and we have ln of x to the negative 1, and x to the negative 1 is 1 over x. So we have plus some constant. So once again, we get ln of c over x. 1 over x times c is c over x. So we'll get ln of c over x. Now, this right-hand side is a little bit more difficult. You have to remember your Calc 2 integrations. This is going to be a partial fraction problem. You basically, there's an understood one on top. You basically want to write this fraction as something over u plus something over u plus 2. And since both of these somethings, the u plus 2, are of degree 1, we go down 1 degree. Whatever degree they are, we go down 1. 1 less than 1 is 0. And a 0 degree is just a constant. Call it a, and over here another constant. Now, if you have these two fractions, you want to write them in a common denominator. The common denominator will be u times u plus 2. In fact, you would multiply this bottom by u plus 2 and the top by u plus 2, which is basically multiplied by 1. Multiply the top by u and the bottom by u. Now, both of these fractions have the same denominator. The numerator is au plus 2a, au plus 2a plus bu. I can combine the u, so I have 2a plus a plus b u's. I just added the number of u's I have. I have a, somebody gave me b more. And this is all over the denominator. Now, if two fractions are equal, and they have the same exact denominators, then the numerators have to be equal. 2a plus a plus bu must equal 1. For 1 is the same as 1 plus 0u. That is, this must be 1 and that must be 0. Well, if 2a is 1, a is a half. 2 times a half is 1. And if a plus b is 0, and we know what a is, b is just the negative of a. It's negative a half. Because when you add a and b, when you add these, the left side gives you a plus b, and the right side is 0. Okay, so now we know a and b. I know, so let's try to clean this up just a little bit. I know that a is 1/2. I know that b is negative 1/2. Negative 1/2. So I have the integral of 1/2 over u minus 1/2 over u plus 2 du. The 1/2 can factor out. So I get 1 over u minus 1 over u plus 2 du. As the half. Now the integral of 1 over u du, that's ln of u, minus the integral of 1 over u plus 2 du is ln of u plus 2. So what's in here is ln of u over. Because when you divide, when you subtract, when you have ln of one thing minus ln of another thing, you have ln of the fraction. What's the half in the front, which I'll bring up as the power. So this is equal to ln of u over u plus 2 to the half. And everything that I'm erasing was basically just the Calc 2 integration. They're partial fractions. You have to remember all techniques of Calc 2. You have to know that the ln function, which looks like this, is a one-to-one function. There's only one time you hit that number, and that's only for this. ln of only that value gives you y. And that's always true. To get this value, you have to take ln of x star. ln of x star gives us y star. It isn't like the function comes down and you say, wait a minute, there's another x. There's another x value. X double star, where ln of x double star also gives you y. ln of x gives you y, and ln of x squared, x double star gives you y. No, the ln function does not go like that. It's strictly increasing. It's a one-to-one function. That is, if ln of this equals ln of that, then this and that are equal. C over x is equal to the square root of u over u plus 2. U, what is this u stuff? Well, we said that y was ux. So y over x is u. So all I did was divide by x, and then I get u. So divide the y by x, get y over x. Okay. So this becomes y over x over x plus 2, the square root of that. Now if I multiply each of these terms by x, they'll kill off all the denominators. Y over x times x is y. Y over x times x is y, plus 2 times x is 2x. So I have that c over x is equal to y over y plus 2x square root. Now we can try to solve this for y. If I square both sides, I square the c, I get a different c over x squared. I square the right side, I get this. I'm going to write that on the next page. C over x squared is equal to y over y plus 2x. If I cross multiply c times that, I get cy plus 2cx is equal to that product, yx squared. I'll bring all the y's to the right side. So the plus 2cx stays, and when I bring this over, I have yx squared minus cy. Well, by design, they all have y's. So when I factor out the y, I get y times x squared minus c. This is 2cx. One last step and we are done. Divide by x squared minus c. We get that y is equal to 2cx over x squared minus c. Okay, let's try one more problem like this. This one will be slightly different. It will have an initial condition, which means that we will be able to solve for the constant of integration. You are told that the y value of 1 at 1 is e. This is an x value, and that's a y value. And I'm also giving you that this is a homogeneous. That equation is homogeneous. So I'll let y equal ux. You know, maybe we'll be bold. We can always use that x is vy. How about we use that one? Differential of x is dx equals the differential of the first times the second plus the first times the differential of the second. So we're going to use that substitution, this substitution, which means this. And I didn't mean to put that equal sign in the middle. Okay, so this time we're changing x's. So y is y. For dx is y dv plus d dy plus x, which is vy, times ln of x, but x is dy, minus ln of y, minus 1 times dy is 0. Now, let's look at what's in this bracket down here. You have ln of vy minus ln of y minus 1. Well, ln of vy is this being a product, I can say it's ln of v plus ln of y minus ln of y. That's going to cancel out, minus 1. So it's ln of v and then take away 1. So I'm going to put that in here. It's ln of v minus 1. Let's distribute over here. we get y squared dv plus yv dy plus vy ln of v dy minus vy dy. This is 0. These three are all dy. And this is add yv dy, and this is take away yv. Remember, vy is the same as yv. Alright, so I took it away. So now I have that y squared dv plus vy ln of v dy is 0. You can separate things here if you like. But let me bring this to the other side. So we have plus vy ln of v dy is negative y squared dv. The factors are v times y times ln of v times dy equals negative y squared dv. So I'm just going to keep the dy and the dv's right where they are. The v, I'm going to cross the division line, put it in the bottom. So I want it on the side that has v. The y, it can stay right where it is. The ln of v is on the wrong side. It's in the numerator, so I cross the division line and I put it in the denominator. The dy is perfect. The negative y squared, I can leave the negative if I want, but I won't. I'll bring down the whole negative y squared. Now, this is what I get here. So let me just write in here. That's going to be negative 1 over y. We have negative 1 over y dy. And this is equal to dv over v times ln of v. I was thinking that wasn't doable, but it certainly is. Now, if it wasn't doable, so we want to take the integral of both sides. If one of these integrals is really, really hard, or both of them, then maybe we shouldn't have used that substitution. Maybe we should have used y equals ux. But this one is fine. We have negative 1 over y dy, negative 1 over y dy, and I think the other side was du over v, wasn't it? dv over v times ln of v. Make sure. Okay. I'm going to integrate both sides. And we integrated this left side many times, possibly with different letters, but nonetheless, we get ln of c over y. Now, the right side. If I say let u equal to ln of v, well then du would be 1 over v dv, or dv over v. Well, let me write this integral on the bottom. Isn't it dv? Can I rewrite this or think of it as dv over v times 1 over ln of v? Now dv over v, du. Times 1 over ln of v, I'm calling that u. Ooh, I know this integral. That integral is ln of u. But u is, and no random guessing, u is ln of v. So we have ln of v. Don't think that for a moment that has ln in it. You have ln of one thing is equal to ln of another thing. So these things must be equal. And v, if x is vy, dividing both sides by y, we get v is x over y. So this is really ln of x over y. So now let us try to solve this. Remember please that ln is shorthand notation for log base e. So e to this, e to the c over y is equal to x over y. Multiplying both sides by y, we learned that y e c over y is equal to x. But if I remember correctly, we're told that y of 1 is e. We're told that y of 1 is e. So y is e. So we have y times e to the c over y is equal to x, which is 1. There's an understood one here. In multiplication, if the bases are the same, keep the base and add the powers. Now, you should know that e to the 0 is 1. E to the 0 is 1. So 1 plus c over e must be 0. So this must be negative 1. After all, 1 plus negative 1 is 0. So c over e is negative 1. Fraction is negative 1 when the top and the bottom are not equal, but they differ by signs. C is negative e. So I'm going to write the answer right in here. Oh, no, I'm going to write the answer right there. C is negative e. So y e to the negative e over y is equal to x. That's the solution for the differential equation. Here, you will not be able to solve for y. At least not easily. I suspect you could for the simple reason if I would have said that y was ux, I'm pretty sure that we would have gotten that y was some function of x. Here, we got that x is a function of y. And since, if I'm correct, that you can solve, remember, these two equations have to be the same. And if I can get y to be a function of x down here, well, then I should be able to do the same thing up there. We're now going to talk about solving a new type of problem, still using a substitution. These are called Bernoulli equations. Bernoulli's equations. An equation of the form I'm about to write down is Bernoulli. And this power of n is any number. any number. Now, if n is 0, if n is 0, you get y to the 0, which is 1, and g of x times 1 is just g of x. This is a linear equation. This is linear differential equation where n is 0. But what if n is 1? If you have dy dx plus p of x is equal to g of x, something's wrong here, I'm so sorry. There's supposed to be a y here. P of x times y. Now, if n is 1, you just have y to the 1, which is y. Now, I can bring this to the other side, and I have dy dx plus p of x times y minus g of x times y, and that equals 0. But I have a y in both of these. I can factor out the y's. I have p of x minus g of x times y. The thing is when you subtract two functions of x's, you just get a function of x. Call it q of x times y equals 0. This is also a linear equation where n is equal to 1. And in fact, this is a homogeneous linear differential equation because the right side is 0. So basically, we want n not to be 0 and n not to be 1 to use the technique of Bernoulli equations. Because we don't need any new techniques. Basically, Bernoulli has a substitution that converts these nonlinear differential equations of this type in front of us into linear. Okay, the substitution is that u is y to the 1 minus n. That's the substitution. So let's get right into a problem. Suppose you have x times dy dx plus y, and this is x squared y squared. Now, to get this to be Bernoulli, the first thing is you just need dy dx, not x times dy dx. So what I'm going to do is I'm going to divide every term by x. And then I get dy dx plus 1 over x times y. X squared over x is x times y squared. Now this is exactly Bernoulli. Here is dy dx plus p of x times y equals to g of x times y to a number. N is 2. So the substitution we're going to make is u is equal to y raised to the 1 minus 2, where 1 minus 2 is negative 1, and y to the negative 1 is y. So u is equal to 1 over y. If I take the reciprocal of u, I get 1 over u. If I take the reciprocal of what it equals, I get y. That's the substitution we're going to make. Okay? If I take the derivative of the right side, because I need dy dx, with respect to x, the derivative of y is dy dx. Take the derivative of the other side. The derivative of 1 over u is 1 over u squared. It's in terms of u with respect to x. For the record, the derivative of y is 1. It's in terms of y with respect to x. And I don't need to write that 1. So negative 1 over u squared du dx, that's dy dx. So instead of dy dx, I'm going to write negative 1 over u squared times du dx plus 1 over x times y. So y is 1 over u is equal to x times y squared. I square the right side, I get y squared. I square the left side, I get 1 squared or 1 over u squared. Okay. But I want to get this to be a linear equation. So I'm going to I want du dx to be alone. I don't want negative 1 over u squared. So I'm going to multiply by negative u squared. I'm going to multiply every term by negative u squared. In the first term, this cancels out, and I just get du dx. The second term, this times negative u squared is going to be negative. So this plus becomes a negative. You get 1 over x, and u goes into u squared, u times, equals to, that's going to cancel to 1, negative 1. So you have x times 1, which is x, times negative 1 is negative x. Now this is a linear equation. Usually we have dy dx plus p of xy is equal to g of x for linear. But it's just alphabet soup. Instead of y's, we call the variable u. So this is, that there is my p of x, and that there is my g of x. So Bernoulli is a really smart dude. He made this non-linear equation into a linear equation. We have now that du dx minus 1 over xu is equal to negative x. So p of x is negative 1 over x, and g of x is negative x. And we're done. We know how to solve this. Just remember that y was 1 over u, or u was 1 over y. Remember, u was 1 over y. Okay. Because somebody asked you to solve an equation that has y's and x's, and you give the answer that u equals x squared plus 4, you're going to be like, what is this u? Okay. So nonetheless, u is going to be the integral of g of x e to the integral of p of x dx dx. The bottom is just e to the integral of p of x dx. And g of x is negative x. E is the integral. P of x is 1 over x dx dx. The bottom is just e to the integral of negative 1 over x dx. We've done this a few times in the recent past. This negative sign can come out in front. You get 1 over x dx. There's the minus. But this integral is well known. It's ln of x. In fact, it's negative 1 times ln of x, which is ln of x to the negative 1, or ln of 1 over x. And for the record, e to this integral, e to the integral of negative 1 over x dx is going to equal to e to the ln of something, and e to the ln of anything is just the anything. So, what I get is the following. Negative integral of negative x times this. Well, that we just worked out. It's 1 over x, the integral dx, all over this, which we just worked out, and we discovered it's 1 over x. Okay, let me get rid of this side work. This product turns out to be negative 1. Negative 1 dx over 1 over x. Well, the integral of negative 1 is negative x plus a constant divided by 1 over x. Well, instead of dividing by 1 over x, you can multiply by x. And remember, this is what u is equal to. U is equal to negative x squared plus cx. Personally, I'd rather write the positive term first. But u was 1 over y. This was 1 over y. I take the reciprocal of this, I get y. I take the reciprocal of this, which is understood right now to be over 1, and I get 1 over cx minus x squared. Okay, let us try another Bernoulli type problem. Suppose you have that xy squared dy dx is equal to y cubed minus x cubed. They even tell us an initial condition, which means we can even solve for the constant. Now, if this is going to be Bernoulli, it's got to be almost, whatever that means, it needs to be almost linear. It needs to be almost linear. What's the big difference? I can multiply the right side by y to the power. But I better have dy dx. Well, that's pretty simple to get dy dx alone. Just divide by xy squared. Divide by xy squared. Divide by xy squared. And over here, you just get dy dx equals 1 over x. Now y cubed over y squared is y. Very interesting. Minus, you get x squared over y squared. Now, if I bring this over, we're in business. dy dx is equal, dy dx minus 1 over x times y is equal to negative x squared, and I'll say y is a negative 2. dy dx plus p of x is that times y is equal to a function of x times y to a power. Power is negative 2. Now we know the substitution is u is equal to y raised to the 1 minus n. So it's 1 minus n. N is not 2. N is negative 2. So it becomes y to the 1, which is y. sorry. 1 minus a negative 2 becomes 1 plus 2, which is y cubed. So u is y cubed. Whenever I see y cubed, I put u. Now if you like, you can raise y cubed to the third power, and when you multiply 3 times the third, you get 1. Y to the 1, or just y. And you do the same to the left side. You raise it to the third. So y is u to the third. Whatever you prefer. Now, okay, so I'm going to kind of get rid of this. Okay, here you're going to get 1/3, taking the derivative. 1/3 u, make that power 1 less. You get negative 2/3 du dx is equal to derivative of y, which is dy dx. So this piece becomes 1 over 3 u to the 2/3. I can put this in the bottom as u to the 2/3 du dx minus 1 over x times y, where y is u to the 1/3, is equal to negative x squared. I'll even say over y squared. If I square the left side, I get y squared. So if I square the right side, I get y squared. So I have to square the left side, which will be u to the 1/3 times 2, or 2/3. U to the 2/3. Now, I want to just have du dx by itself, all by itself. So, I'm going to multiply it by 3u to the 2/3, and all of that cancels. Multiply this by 3u to the 2/3, 3u to the 2/3. Here, I just get 1 times du dx, which is du dx, minus 1 over x times 3, that's 3 over x, times u to the 3rd times u to the 2/3. You add the powers, you get 3/3 or 1. You don't have to say u to the 1, it's just u. And this is equal to, well, this cancels out, and you get minus 3x squared. Now this here is linear. This is my p of x, and this here is my g of x. And I want to write down a couple of things. Y of 1 is 2, and y is u to the 1/3. And the reason I want to do that is because I need this space. So we have, after making this substitution, first writing that equation in the form of, or Bernoulli equation, and then making the appropriate substitution, we got down to a linear differential equation. And linear is a piece of cake. U is equal to the integral of g of x, e, times e to the integral of p of x dx, all over e to the integral of p of x dx. Well, g of x is negative 3x squared times e to the p of x. P of x is negative 3 over x. the integral of negative 3 over x dx over e to the integral of negative 3 over x dx. Well, first let's solve that. What is the integral of negative 3 over x dx? Well, if you pulled out the 3, you have the integral of dx over x, which is nice and easy. It's ln of x. Bring in the negative 3 as the power, you get ln of x to the negative 3. But I don't really want this integral. I want e to this. I want e to that. And e to the ln of anything is the anything. Okay? So I have the integral of negative 3x squared times this integral which we just solved. Is x to the negative 3. X to the negative 3 dx. And I divide this by this, which is x to the negative 3. Okay. The negative 3 I'll pull out in front of the integral sign. You add these powers, you get x to the negative 1, which is 1 over x dx. In the bottom, you have x to the negative 3. You have negative 3 times this integral. Is ln of x plus a constant plus ln of c divided by x to the negative 3. Okay, let's clean this up and we will be fine. Remember, this is what u equals. So u is equal to, I can bring that up as the power, ln of x to the negative 3 plus ln of c over x to the negative 3. So that top will be ln of c times x to the negative 3 over x to the negative 3. Now, this product is just c over x cubed. And this is really 1 over x cubed. Instead of dividing by that, you can multiply by the reciprocal. So that is what u equals. But u is y cubed. Okay? So y cubed is equal to this. X cubed times ln of c over x cubed. Now when they tell you y of 1 is equal to 2, the 1 is the x and the y is the 2. Okay? So 2 cubed is equal to 1 cubed times ln of c over 1 cubed, as opposed to c over 13. Now 2 cubed is 8. 1 cubed is 1 times what's in the box is times what's in the box. And what's in the box is ln of c over 1. 1 cubed is 1 and c over 1 is c. Okay. Now remember, ln of c, ln is shorthand for log base e. So e to the 8 is equal to c. E to the 8 is equal to c. Okay? So I update my equation. I update my equation. Y cubed is equal to ln of e to the 8 over x cubed. Now you can leave it like that, but I wouldn't personally. You could say this is ln of e to the 8, which is 8, minus ln of x cubed. So y cubed is equal to ln of e to the anything is the anything minus ln of x cubed. Now you can leave it like that, or you can take the cube root of both sides. So y is equal to the cube root of 8 minus ln of x cubed. Okay, of course, there's a little error here. It said very clearly that y cubed was x cubed times ln of c over x cubed. And we learned that c was e to the 8th. But I just failed to write down y equals x cubed times ln of e to the 8 over x cubed. Now that in the brackets is ln of e to the 8 over x cubed. But we still have the x cubed in front. Now when you take the cube root of a product, you take the cube root of the first, which is x, times the cube root of the product, which I don't know. So there is your answer. We're off by a factor of x. I'm sorry. Okay, the instructions for this problem is to use the Bernoulli method. I hope that's very clear. There's an understood negative 1 here. So we have dy dx plus a function of x, which is just a constant, times y, is equal to a function of x times y to the 2. So n is 2. This fits like a glove. We didn't have to make any adjustments. So we know that the substitution is going to be u is equal to y raised to the 1 minus 2, which is y to the negative 1, which is 1 over y. So u equals 1 over y, or y equals 1 over u. So then, taking the derivative of the left side, we get dy dx. With respect to x, I'm taking a derivative. The derivative of 1 over u is negative 1 over u squared times du dx. So dy dx is negative 1 over u squared du dx minus y, which is 1 over u, is equal to e to the x times y squared. You square y, you get y squared. You square the other side, you get 1 squared over u squared. And multiplying by 1, we don't have to bother. Now, I'm going to multiply each of these terms by negative 1 over u squared. Negative u squared. Negative u squared, and negative u squared. The u squares cancel out to negative 1, and negative 1 times negative 1 is 1, times du dx is du dx. Minus a minus, we just get plus u is equal to negative 1 times e to the x, which is negative e to the x. There's an understood 1 here. That tells me, so this here is linear, where p of x is 1, and g of x is negative e to the x. Wonderful, I know the answer to this already. U is equal to the integral of g of x times e to the integral of p of x dx over e to the integral of p of x dx. Well, e to the integral of 1 dx, well, the integral of 1 dx is x, so it's e to the x. So the bottom is e to the x, the top is negative e to the x, that's from here, times this, which is e to the x dx. So for the top, at least, we get negative, which I'll pull out in front, the integral of e to the 2x dx over e to the x. Negative, the integral of e to the 2x is e to the 2x over 2 plus a c, all over e to the x. We'll multiply each of these terms by 2 to kill off that 2 in the bottom. We get e to the 2x plus 2c, which is just c, over 2e to the x. And this is what u equals. But u is 1 over x. I know it is. I'm not going to just randomly make this stuff up. It's right there. U is 1 over y. I take the reciprocal of this, and I set it equal to the reciprocal of that. Top will be 2e to the x. Now, I hate starting off with a negative, so I'm going to go plus c minus e to the 2x. And there's that answer. Okay, let us try one more. Suppose you are told to solve this using the Bernoulli method. Now, one way you should start thinking maybe these are Bernoulli is you have a function of x times y, and then you have a function of x times y to some power other than 0 or 1. But I want to get dy dx alone, so I'm going to divide by x. I'm going to divide by x, and I get dy dx minus 1 plus x over x times y is equal to 1 times y squared. That's Bernoulli. And that's n. So u is y to the 1 minus n, which is y to the negative 1, which is 1 over y. So u is equal to 1 over y, or y is 1 over u. And dy dx, take the derivative of that with respect to x, is equal to the derivative of that, which is negative 1 over u squared, with respect to x. It's in terms of u with respect to x. The derivative of y is 1. It's in terms of y with respect to x. And we don't have to bother multiplying by 1. Okay, dy dx is negative 1 over u squared du dx minus 1 plus x over x times y, where y is 1 over u, is y squared. It's 1 squared over u squared. And 1 squared is 1. Okay, now I take each term and I multiply it by negative u squared. So this cancels. Negative u squared, negative u squared. And I get du dx plus 1 plus x over x times u is equal to negative 1. This here is a linear differential equation. Now the answer. P of x is 1 plus x over x, which is 1 over x plus x over x, and g of x is negative 1. Now we'll try very hard to get the rest in here. So u is the integral of g of x times e to the integral of p of x dx over e to the integral p of x dx. Well, what is e to the integral of p of x dx? Well, p of x is 1 over x. So let me say 1 plus 1 over x. It's 1 plus 1 over x dx. So it's e. The integral of 1 is x, plus the integral of 1 over x is ln of x. Now why did I want to write the 1 first? I didn't want to have e to the ln of x plus x. Some people might think it's e to the ln of 2x, because x plus x is 2x. But now, this is e to the x times e to the ln x. After all, we're multiplying, the bases are the same, so you get one base, the common base, and then you add the exponent, x plus ln of x. And you go, oh yeah, he must be right, that's what it says. Now, this here is just x times e to the x. So we get g of x, which is negative 1. I'll pull out right in front the negative 1, times this part, which is x e to the x dx, all over this part, which is x e to the x. Okay, let's erase this. That was somewhat scrap work. Now, to solve this top one, in fact, I'm actually going to put that negative inside. It's a product of two terms, one of which, if I take the derivative, first write it down, if I take the derivative of enough times, I'll get to 0. The other one, I'll integrate e to the x. I integrate e to the x. I get e to the x. Integrate that again, I get e to the x. So for this top, the answer is this product. Now, minus that product. Clearly, e to the x is in common. So it's this product, negative x, minus this product, which is going to be negative 1, plus a constant, x e to the x. Okay, now this is what u equals, but u is 1 over y. So I take the reciprocal of both, and I get x e to the x over e to the x. Instead of negative x plus 1, I'll write 1 minus x plus c. And this completes the section on substitution.